Start recording. I'll go ahead and use this class for my international students crew so they can follow along with at least one of the classes. So you guys are the lucky ones today. So for today's lesson, we're going to do a few different things. First, just a couple quick reminders about due dates, and then a brief comment on the test, and then we'll spend some time towards the end of the period during the work portion where you can ask some more specific questions on the test. Then we're going to take some notes on kinematics, continuing on with the understanding of acceleration. And I'm going to tie in a few things to that summary sheet exercise that Carter was asking about a few minutes ago before we officially started. And then at the end, just time for you to work on either doing test corrections or finishing up the summary sheet or continuing to work on positive physics. Just time to work, hopefully, for the last half hour-ish. So the reminders, the summary sheet's due tonight. And I've had a few students ask if it's better to do them before you come to class the day it's due or better to do it after class. My encouragement is always to try to have it done as much as you can before you come to class the day that it's due, even though it's not due till later that night. That way you know what questions you have. So in class, like Carter did earlier, just ask a question, we can have a discussion and make sure you know what's going on. So I would encourage that, but it is obviously not due until the 11:59 time, unless I specifically give otherwise. I think there's only been one time this year where I specifically said, please try to have this done before you come to class. Generally, that's my recommendation, but it's not the expectation. So the summary sheet's due tonight before midnight Pacific time, and then the positive physics unit 2 assessment is due by Thursday night. And remember, it's the assessment, not the work. You can do as much or as little of the work section as you choose. You could do none of it if you want, if you're okay with just doing the assessment by itself. But the work section could help you. So the work section is not required, but it is just to help you. All right, so those are the reminders. Test I have scheduled for the last part of class today to give you some specific directions for how to do the corrections and how to submit them. But just wanted to give you some timeline for knowing what to expect. Those corrections will be due not this Friday, but the following Friday, October 16th. And so you've got basically 2 school weeks to get the corrections done. Now, if you turn them in next week, they won't factor into your quarter grade because quarter grades end this week, and I have to have grades turned in Monday or Tuesday next week. So I would need them turned in by Friday if you want them to go in your quarter grade. But they're not technically due until the following Friday, the 16th. And that is the same for a retest. If you would like to do a retest for the Unit 2 exam or assessment, you can do that. And same, you just need to get it done by not this Friday, but the following Friday. But if you want it to go on the quarter grade, then you would need to get it done this week. So you have 2 weeks of school. I know next week you don't have many school days, but you have that 2 weeks of time, basically 2 school weeks of time to schedule it and get it done. I do have 4 dates chosen for retakes. And then I'll have to work with the international students individually through the testing center. But for you guys, the 4 due dates for retakes would be, or the not due dates, but optional dates, Wednesday this week or Thursday this week. And then next week, you guys don't have school Monday through Wednesday, so just Thursday and Friday next week. So that's 4 days to choose from, Wednesday or Thursday this week, Thursday or Friday next week. And I just decided to make it 3:30 to 4:30 every one of those days, so it's just consistent, easy to remember. I put an announcement on the bulletin board for class. So if you look at the announcements in the top right-hand corner, all those dates and times are there as well. But if you need a reminder, you can look there on that bulletin board and see that timeline for the retest. In terms of how you do the corrections and all that, we'll talk about that later in the class because I'll be giving you specific directions and actually helping you get going on that. But any questions about due dates or timelines? All right, let's go ahead and jump into the lesson today. And we're going to start with a couple things that may help you wrap up some questions you could have on the summary sheet. Depending on your math background, there might have been a couple questions on the summary sheet that were a bit confusing to you. And so if that's the case, I wanted to talk about some of those math concepts together today. So the first concept that is brought up on, I think it's page 4 in that summary sheet, is the idea of tangent. And we've talked about slope of a line and what the slope of a line tells us. But for instance, the part I'm thinking about, it's referring to position time graphs. And just generally speaking, what is the slope of a position time graph?
The velocity?
Velocity, yeah. So the problem is if we have, like we did in the moving man lab, if we have a position time graph that's curved, there's no single slope. There's no one number for the slope. It's changing because the velocity is changing in that scenario. The slope is changing. And a couple people on that exercise wrote there is no slope. But I think it's better to say the slope's constantly changing because a parabola does have a slope at any given point. It's just not a constant slope. It's an ever-changing slope. And the reason the slope is ever-changing in this position versus time scenario with Motion Man was because the velocity was ever-changing. All right, so back to the concept of tangent now, because in the context of the worksheet, it's talking about tangent and slope and position time. Well, on a position time graph, you could have a quadratic relationship. You could have something that's accelerating. So to find the slope, we have two options because there is no single slope, but we could use a tangent to find the slope at one point. A tangent is specifically a line that touches a circle or a curve at one point. So I've got a few examples here. On the top left, you can see I've drawn, or someone has drawn, a tangent to a circle. And one nice thing about when you draw a tangent to a circle, the point where that tangent touches the circle, it always only touches at one spot. That's part of the definition of a tangent. Because it only touches at one spot, that one spot, if you draw a line straight to the center of the circle, will create a perpendicular angle there. That's going to be really helpful for us when we learn rotational movement next semester. So a little preview already. And this second one, this is like a parabola, so it's a quadratic relationship. And so maybe starting at time 0, this would be potentially the right side of this parabola could be a position time graph for something that's increasing in its velocity in a quadratic manner. And so we can't say that there is a slope. We can say that at a given point in time, there is a slope, and the tangent would just be a straight line that touches that parabola in one spot only. And if we find the slope of that tangent line, it would be the slope at that point. So if it's a position time graph, it would be the slope of the parabola or the position time graph at that instant. So since the slope of a position time graph, Lily just told us a bit ago that that is velocity. If it's the velocity at one point, what would we call that?
Instantaneous velocity?
Yeah, instantaneous velocity. Good. Now you can see that on this third picture, the big one over here on the right, we can draw tangents wherever we want. And they've drawn a bunch on this parabola. So you've got this orange one that connects to the parabola over here on the left side. You've got the green one and all the blue ones that connect on the right side. And every one of those straight tangent lines has a slope because they are straight. And wherever they touch the parabola, that would be the instantaneous slope at that point. And if it's a position time graph, then that would be the instantaneous velocity at that point. So on the summary sheet where it's asking you to think through the slope of a position time graph specifically as related to a tangent line, it would be the instantaneous velocity. It's the velocity at that single point in time. So hopefully that helps with that. Before we go on to secants, any questions about tangents? All right, and some of you, this is old hat. You've learned this in other math classes, but for some of you, maybe new. All right, for a secant is when we draw a straight line that touches a curve in two spots only for a parabola. So we're looking at a line through a parabola that specifically touches 2 points. Now, if you look at this first one on the left, this line obviously has a slope. This secant line has a slope, but it is not the slope of the parabola where it touches at the top point, and it is also not the slope of the parabola where it touches at the second point. Instead, it's the average slope between those 2 points. Okay, so when we draw a secant line, because there's 2 points, it doesn't tell us anything instantaneous. It tells us an average. So you can see that here we have a slope that's rising, but only for a short period of time, and then it starts to fall and increases rapidly. So overall, the average from this point on the left to this point on the right would be a downward average, a negative average. And the one over here on the right, we've got another secant. So the one on the left, we've got one spot on one side of the apex and one spot on the other side of the apex. But in the one on the right here, they're both on the same side of the vertex. And so those 2 points align a lot more with the shape of the parabola, but they're still not instantaneous values. The slope of this blue secant line is the average slope between the 2 points on the parabola. So if it is an average slope, if I'm talking about a position time graph, what would the secant tell me? The slope of the secant.
Average rate of change.
Yeah, the average rate of change. And if it's position time, what's the word that defines that rate of change for a position time graph?
Average velocity.
Yeah. So if we find the slope of a secant line for a position time graph, that slope would be the average velocity. So a tangent touches it at one point, giving you the instantaneous velocity at that instant, but a secant touches at 2 points, so it just helps us find an average velocity on a position time graph. So that's what I was going for there. Wanted to see how many of you had some background math and could maybe think that through. If we had had a little bit more time together in the classroom, that would have been a situation where I would have put you in groups and have you brainstorm it a bit. But it's a little bit harder to do that we have much fewer minutes of class time with our current situation. So I've got to find different ways to cover things. So, but that is secant and tangent. Let me just show you a couple other pictures to show you a secant and a tangent together on a particular curve. So here we've got this red curve, this parabolic shape, and then we've got a green secant line. So if I found the slope of the green line, it would tell me the average slope of that parabola between the 2 black dots. And then we've got a blue tangent line. If I found the slope of the tangent line, it would tell me the slope at that point 113, point P. So the tangent line gives me a slope at a single instant. The secant gives me an average between the 2 points that create the secant. Here's another example where they're both drawn on the same curve. You can see the secant line has its 2 points, and so its slope gives me the average slope of the parabola between those 2 points. And then over here, we've got this tangent drawn at its single point. If the secant and tangent are parallel, like it appears they may be here, what's true of their slopes?
They're equal.
Yeah, so if they're parallel, their slopes will be equal. So what that would mean is the slope of this secant line, which is the average slope between these 2 points, would be the same as the slope of this tangent line, which is the instantaneous slope at this point. So there is a way you can coordinate the use of secants and tangents together to figure out the slope of a tangent line from a secant line. It's just that the tangent line would have to relate to the secant line in a very specific way. And we're going to look at that here on the last slide of this part. This is a position time graph. Instead of just some generic parabolas, this is an actual position time graph, the blue curving line. So you can see as time passed, the position was changing in a non-linear fashion. So the velocity was increasing. And since the velocity is increasing, the slope of this position time graph is ever increasing. If I draw a secant line, so here it shows me that I'm drawing a secant line between 2 seconds and 6 seconds. So what does the slope of the secant line tell me in this scenario?
The average velocity between 2 and 6 seconds.
Good, the average velocity between 2 and 6 seconds. So not just the average velocity of the whole thing, but specifically between 2 and 6 seconds. Now, I've drawn a tangent line that is parallel. And what do you notice about the single point that the tangent line touches the curve at compared to the secant?
It's the average of the 2 secant points, like the endpoints of the secant line.
Yeah, it's right in the middle. It's the midpoint of that secant. If the secant starts at 2 and ends at 6, the parallel tangent would touch at 4, right in the middle. So the trick of this is if you're trying to figure out tangent lines, because if you think about it, if if you're trying to eyeball a tangent line, you're trying to draw a straight line that only touches a curve at one point. And there are geometric constructs you can do to draw it properly. And if you remember those from geometry, you could use those skills. But generally speaking, we don't want to take the time to do that. And if you're just eyeballing a tangent line, if you're just off by a little bit, it could give you a very drastically different slope. So while tangent lines do give us instantaneous velocities, they're not great to do practically speaking because they're hard to do well unless you take the time to really do those geometric constructs or use a computer to help you determine them. If you draw a secant, that's easy because it requires 2 points. And if you draw 2 points and draw a straight line with the ruler, the slope of it would be just using those 2 points. So finding the slope of a secant line is simple. And so if you know you want to find the instantaneous velocity at 4 seconds, just draw a secant line from 2 to 6, and it would be the same as the tangent at 4. What other time frame could I choose and still get the same as the tangent at 4? Instead of 2 and 6 seconds for my secant, what other times could I choose and still get the tangent of 4 seconds?
Like 1 and 7.
1 and 7,
3 and 5.
3 and 5, 0 and 8, as long as 4 is the midpoint, right? So you could draw any secant you want where 4 is the midpoint, find the slope of your secant line, and that'll tell you the slope of the tangent line at its midpoint. So we're actually going to go through those steps next week. Today is sort of a foreshadowing of that, but I'm hoping we'll have time in that one period we have next Thursday to actually go back to the moving man activity and revisit that a bit with doing some of this tangent secant graphing. So that's the plan for next week. Any questions about tangents and secants and how they relate to slope and specifically nonlinear position time graphs? All right, hopefully that helps. Do you have any other questions about the summary sheet before we jump into today's notes on acceleration? This is sort of this is actually going to relate. So it's hopefully you'll see the connections now that we've talked about tangents and secants as we go through today's notes. Hopefully you'll see the connections to that, but I'll try to emphasize it as we go. But do you have questions on the summary sheet before we sort of switch gears a little bit? All right. Some of you might not have heard Carter's question earlier. He was asking about the area under a position time graph. And he mentioned that thinking about that area gives you the units meters times seconds. And he didn't really know of anything that goes to meters times seconds. Like if it was meters per second, that would be velocity, but meters times seconds doesn't really seem to be anything that we're familiar with. And so if you didn't hear that conversation, basically what I told him is, yeah, what he said is exactly what I wanted you to learn, is that the area under a position time graph really isn't helpful. The area under a velocity time graph is helpful. The area under an acceleration time graph is helpful, but the area under position time graph is really not very helpful. And that's just something I wanted you to kind of think through and determine. So if you missed that conversation, that was kind of before class started, actually. Just wanted you to have that thought. Do you have a question, Lily?
Yeah, it's on the summary sheet. So we just talked about how to find the instantaneous velocity with the tangent line. Is that like correlated to the last question on the page 4? How can you find the instantaneous velocity in a position versus time graph? You would use a tangent line if it's a nonlinear graph.
Yep, perfect.
Okay.
If you're having any questions about the models, mathematical models that it asks you to come up with, think about drawing a straight line graph and using slope intercept. So probably most of you connected that, but if not, think about how that would work. Okay, just like if you're graphing position in time, what would be the y, what would be the x, what would the slope tell you? I'm just looking for some generic, like, if it's position time, then x is my y-axis and t is my x-axis and the slope is velocity. Just trying to get you to think through some very generic patterns there, just using slope intercept form. So you're not going to actually have a number for the slope or anything. I'm just looking for variables, basically. All right, if you have other questions, feel free to bring those up at the end of the class during work time, but let's jump into some slides about velocity and acceleration and extend our knowledge just a little bit. So the first thing I want to talk about is average velocity. And average velocity can be really helpful, and there's two ways to find it. It depends on what we know from the problem. If we know the displacement and we know the time, just taking displacement divided by time is the average velocity. That's actually the definition of average velocity. Change in position over change in time, or displacement over time. But sometimes we don't know how far it went, and we may not even know how long it took. So if we don't know the displacement and or we don't know the time, there's a second way to find an average velocity, and it's much more simple in terms of just basic mathematics. All of you have found averages before since elementary, probably. You learned how to do an average. So if I was finding the average weight of two people, I would add their weights and divide by 2. If I was finding the average grade on a test for your class, I would add all your test scores together and divide by how many students, right? I mean, you know how to do an average, you've learned that. So that's another way we can find the average velocity. If we know what the velocity started at and we know what the velocity ended at, we just add those together and divide by 2. So the final velocity plus the initial divided by 2 would give us the average. So there's two ways to think about averages, and it can be pretty helpful. Now, what would have to be true for the average velocity and the instantaneous velocity to be equal in magnitude? What would have to be true for the average velocity and the instantaneous velocity to be equal in magnitude?
The average velocity's middle point has to be the place that you're trying to find the instantaneous velocity.
Good, that's one way. That's the hard one. Yeah.
And then doesn't the velocity have to be constant? Like there's no the acceleration is nothing. It's the same.
Good. Yeah, you guys nailed it. So the way Haley said it, if there is no acceleration, then the constant velocity and the instantaneous would be the same. The average and the instantaneous would be the same. And if there is an acceleration, then what Jackson said is correct. Then we have to look at the midpoint of those averages, that final and initial velocity, and it would tell me the instantaneous at the midpoint. Good. Very nice. All right. Now in math class, when you have two equations like this and they're both set equal to the same variable, what are you generally going to do at some point?
Substitute.
Either substitute,
Eliminate.
set them equal to each other, right? I mean, we do those kinds of things in math, right? We're going to do a couple of those things here after we practice some average velocities math questions. So in the chat, got a couple questions here. Here's the first one. Once you figured it out, put your answer in the chat. Starting from rest, you accelerate to positive 20 meters per second in 4 seconds. What is your average velocity? We have a lot of agreement so far. And this is one of those questions that sometimes students will read fast and answer quickly, and they'll come up with the answer of 5. They'll just see that 20 and that 4, and they'll just divide right away and say it's 5. But remember, the average is just taking the sum of the two, the beginning and the ending. It began at 0 because it says from rest. It ended at 20. So 20 plus 0 divided by 2, because we're only looking at 2 velocities. So the average is, as you all wrote, positive 10 meters per second. Let's try another one. Starting with a velocity of positive 12 meters per second, you accelerate to 48 meters per second in the positive direction over a 6-second time interval. What's your average velocity? All right, good. Seeing a lot of good contributions here in the chat. So 48 meters per second plus 12 meters per second divided by 2 gives us the positive 30 meters per second average. So the 6 seconds is unnecessary. We don't even need that number, right? Question, Gavin?
Yeah, sorry, your screen share for some reason has just been like flickering on my screen. I don't know if anyone else has been seeing it, but I don't know if you might want to like stop sharing and then try again. Or I don't know if anyone else is seeing that though.
Is there anybody else having that problem? No.
Oh, maybe it was just
Yeah.
my computer. Okay, never mind.
That's
It was just
right.
going like it was just going like on and off, and it was just like flickering really nasty. So, anyways,
Hopefully that'll discontinue. Thanks for asking, because it could have been a problem that more were having. So, so with this question though, so in this question we don't really need the 6 seconds. It's just it's a distractor basically, right? Like it's a number that they've given us to see if they'll trick us. And College Board likes to throw distracting numbers at you every once in a while. Now on the next question though, it's the same scenario, but they're asking a little bit of a different question with the same information. All right. So we're still starting at a velocity of positive 12 and we're accelerating to positive 48 in 6 seconds. That's all the same. But now they want to know, how far did you travel in that 6 seconds? So they're not asking the average anymore. They want to know, how far did you go? They want your displacement. All right, seeing a lot of agreement here. The average velocity is defined as displacement over time. So the displacement would be average velocity multiplied by time. And we found the average velocity on the previous slide. And so we can use the time to determine the displacement. So sometimes in a free response question, in fact, not sometimes, almost always, they'll give you a lot of information. And for part A, you have to discern which bits do I need to answer A, and then which bits do I need to answer B. And it's like a multi-step problem. So this might be like an A and a B to a free response, where first they ask you to find the average, then they ask you to find the displacement, and they might then branch it off into other things later. Just trying to introduce you to that concept of how they might design a free response question. All right, any questions from you? Go ahead.
Oh, sorry. So the way that you know it's displacement instead of just distance is because they use velocity, right? Which is why you put like the plus 180 instead of just regular 180.
Yeah.
Okay.
Yeah, since we're using velocities, which are directional, we know the 12 is in the positive direction, the 48 is in the positive direction. So then we know that our displacement would have to be in the positive direction as well. Yeah, any other questions before we move on? I don't want to go too fast if there's something else you want to ask. All right. And in this question, it actually uses the word velocity. But if they had just said the object was moving at positive 12 meters per second, because they put the positive, then you would know they're referring to velocity, not just speed. So that's another reason we want to use those signs. All right, the last topic of the day is the second kinematics equation we're going to learn. I'm just going to let you look at it for a second. If you have printed the physics equation and constant sheet like I recommended a while ago, if you have that somewhere nearby, I would like you to look at that and compare if you have it. The way I'm showing it on this screen is ever so slightly different than the way it is on that formula sheet that College Board provides for you. Now, it's the one side of the College Board handout. The very first one in the top left corner is the first kinematics equation we learned last week. And then right underneath it is this one, the second one that we're learning. So I teach them in order for a lot of reasons, and they follow the same order on that sheet. But how have they changed delta x on the version that College Board has given?
They have a normal x, like x final, and then they add x original.
Good. So delta x is just x final minus x original, right? I mean, that's change in x is just final minus original. So instead of writing it as delta x, they're writing it as final equals the original plus this, right? So they're just rewriting it as solving for final position instead of change in position. The reason I don't typically write it that way myself is I would say at least 95% of the time, maybe closer to 99% of the time, they're not going to ask you final position or initial position. They're going to ask you for change in position. So almost always what we need to find is change in position, not the final or initial position. So rather than using it the way they give it to you, this is, I think, a more practical form of it, because the change in position is almost always what we need. So that's all I'll say about that for now. The downside is that's the form they give it to you in, and that's the sheet you have when you're taking a test. So you need to be familiar with it and be comfortable with seeing the difference. You can write it this way. Like if you're solving a problem for College Board, you can write the equation this way. You don't have to write it the way they did. But that's the only resource you'll be able to look at while you're taking the test, is what they've given you. So I want to make sure you're comfortable with that. Now we're going to figure out where this equation comes from two ways. We're going to derive it graphically first and then algebraically second. So let's start with the graph. Here's the first graph we're going to look at, and this is kind of a quick review of our last lesson. Someone unmute and describe the motion of this object based on this velocity time graph, the blue line.
An object starts at 2 meters per second, travel and keeps a constant velocity for 6 seconds, and then stops.
Okay, good. So the key here, a couple things you said that were really good, but the key here that I want to make sure everyone notices and catches, it's constant velocity, right? There's no changing velocity. Now, from what we learned in our last lesson, what is the, because it says underneath here, area equals length times width, but what does that area represent for a velocity time graph?
The displacement.
The displacement, good. And we went through and we broke that down last week, but just as a quick review, the area under the curve is length times width. So in this case, that would be velocity multiplied by time. And last week we broke down the units and we recognized that velocity is change in position over time. So v times t, if I just multiply both sides of this equation by t, I get delta x equals vt. So the area under this curve is vt by length times width, but vt is displacement. So the area under the curve is displacement. And we kind of proved it with the units as well, that the velocity is meters per second, the time is seconds. So the seconds cancel and give me a unit of meters, which is dimensionally correct. So quick review of what we learned last time. But like Haley said, that means this object is traveling at a constant velocity, and not all things travel at constant velocity, right? And so this is only one way something could be moving and one way we could find the area. So Atticus, what would you say is different about this object's motion? Obviously the graph looks different, but how is the object's motion different here?
I'm not 100% sure. It's a little bit strange to me just because, yeah, I mean.
Let me go back to the previous one. So in this one, like Haley said, this velocity is unchanging.
Yeah.
So how's this one's motion going to be different?
Well, the velocity is increasing over time. But,
good.
Oh, okay.
Yeah, so that's all I was looking for. You might have been thinking I was looking for something deeper, but that's all. Just the velocity in this case is changing over time. And Mark, what do we know about the initial velocity for this one?
It starts at 0.
Yeah, so it was at rest at the beginning. In the previous one, it started at 2, like Haley said, and it continued at 2. But at this one, excuse me, it's starting at 0 and it's increasing over time. But we said that the area under the curve is displacement. So if the area under the curve is displacement in one graph, it's got to be the same in this graph. They're both velocity time graphs, but we don't find the area of a triangle the same way we find the area of a rectangle. So we have to use a different geometry. And I'm sure you all remember that 1/2 base times height is how we find the area of a triangle. So if we think about that, in this case, that would be 1/2, the base is time, and the height would be the change in velocity, right? It went from 0 to whatever that is, 1, 2, 3, 4, 5 meters per second. Does that make sense? That the base would be how long the time was and the height would be how much the velocity changed? And so over here on the left, this A, capital A, is area. This 1/2 base times height would be 1/2 t times delta V. But over here, I've got small a. What's small a?
Acceleration.
Acceleration. So acceleration is change in velocity over time. So here I've got change in velocity. Here I've got change in velocity. So we could do some substitution. This acceleration equation, if I solve it for change of velocity, I just multiply both sides by t. Change of velocity would be a times t, acceleration times time. Now I can substitute this at into the delta v, or in for the delta v. Follow me okay on that? All right. If I do that, it looks like this. The area would be 1/2 t times at, which simplifies to 1/2 at squared. So that would be the area under the curve. But what did we say the area under a velocity time curve tells us?
The displacement.
Displacement. So that area is the displacement. So let's look back to this previous slide here. See this 1/2 at squared? See this vt? Constant velocity, the displacement ends up being vt. Changing velocity, the displacement ends up being 1/2 at squared. So in this problem, I was limited because the velocity has to be constant for this to work. In this problem, I'm limited because it has to start at 0. But what if I have this? What if it's changing and it doesn't start at 0? Well, do you see how this trapezoidal shape is just a rectangle underneath a triangle? And we found the area of this rectangle in the first example, and we found this area of the triangle in the second example. So what would the area under this shape be?
Both of those areas added together.
Yeah, the sum, just add them together. So if I add those together, the area would be VOT for the rectangle part, 1/2 at squared for the triangle part. And because the area tells me displacement, that is the second kinematics equation. So this second kinematics equation is kind of like a Swiss Army knife. It can do all kinds of things. If you have a problem that, like the first one we did, has 0 acceleration, well, if you put a 0 in for the A, it simplifies down to just v times t. You could also have a problem where the initial velocity is 0, like the second one we did. If you put a 0 in for v0, v0, vo, v original, that part cancels. But if you have an acceleration and you have a non-zero initial velocity, then you use the whole equation. So this equation can work for all 3 scenarios. Questions? All right, that is the second kinematics equation and how we make sense of it geometrically or graphically. All right, to finish up, I want to talk to you about how we can make sense of it algebraically. Now, I spent quite a bit of time going through the geometry and the graphing because to me, I think that's conceptually more helpful. The algebra, I'm only going to spend a few minutes on, mainly just because I want you to get the practice of seeing the algebra and deriving an equation, because you will almost always have to, at least once in the free response questions, derive something. All right, so that's why we're going to practice it. So let's jump ahead. What is this the equation for?
Average velocity.
Average velocity. All right. So, Jenny, what if I solved this for delta x? What would delta x be?
Displacement, or the change in displacement.
Change in position, which is displacement, but what would it equal in the equation if I just reworked the algebra and just solved it so that delta x was by itself?
Oh, so it would be delta x equals to vt.
Yeah. So that's my first step, is I just want to rearrange it to get the displacement by itself. Because what I'm going to try to do is create the second kinematics equation. Okay, and the second kinematics equation is set equal to displacement. So that's what I'm going to try to get here. Now, let's see. Jilly, we said on one of the first slides that average velocity could be displacement over time, like we're starting right here. But what was the other way we found average velocity?
Final velocity minus initial velocity over 2.
Good. So since final velocity plus initial velocity over 2 is also average velocity, like I think Haley predicted, we're just going to substitute that in for average velocity. And it becomes 1/2 VF plus VO times T. And then over here on the left, I've just changed delta x into the x final minus x initial, like College Board tends to write it. So we're not done yet, but any questions so far? So mathematically, what do I need to do to the right side of this equation to simplify it further? How do I get rid of this parentheses? Mark?
Distribute the t.
Yeah, we can distribute the t and the half. So we'll use the distributive property, and we get this change in position equals 1/2 VFT plus 1/2 VOT. But if you look at that second kinematics equation that we're focused on today, what does that equation have that this one doesn't have?
Acceleration.
Yeah, this one doesn't have acceleration, but the second kinematics equation does. So we need to figure out a way to get acceleration in here. What does this equation have? What variable does this equation have that the kinematics second equation doesn't have?
Final velocity.
Final velocity. So we need to figure out a way to get rid of this final velocity and replace it somehow with an acceleration. So that's what we're going to do. Here I've just used the commutative property of addition, and I've just put the order backwards. So here it was final first and original second, and I've just changed the order and put original first and final second. And now, what is this equation over here on the right?
First kinematics equation.
Yeah, that's the first kinematics equation we used. So now that has acceleration in it, and it's set equal to VF. So if we substitute this in for VF, we won't have VF anymore, but we will have acceleration. And that's exactly what we wanted to do. So I substitute that in. So now I've got 1/2 times VO plus AT times T. All right. What do you think I'm going to do next mathematically?
Distribute the t.
Distribute again. Good. So if I distribute, I get this. And then what's my next math step?
Yeah.
Combine like terms.
Combine like terms. We're going to add them. Yeah. So I've got 1/2 of a VOT, and I got another 1/2 of a VOT. If I have a 1/2 and a 1/2, that makes a whole, right? So I end up getting this equation. So we solved it graphically / geometrically, which I think is more conceptual and easy to wrap our brains around why that works. And then we've also done some algebra gymnastics here, doing, nothing difficult, a little bit of substitution, a little bit of distribution, a little bit of combining like terms, but nothing really difficult mathematically, but have to be a little creative in knowing what to put where and how to substitute. but we've been able to generate the second kinematics equation, both graphically and algebraically. So again, it's not some mysterious sorcery. It's just math. All right. Now, last bit before we give you some work time. On moving man, in the second part, you had to turn the acceleration on so that the guy would speed up until he hit the wall, right? And your graph for position time was a curve because he was speeding up. And one of the questions says, what's the slope of the position time graph? And most students did what I expected and what I even encouraged is just say, well, the slope was not constant. The slope was changing since it's curved. Some people said it doesn't have a slope, and really it does have a slope. It's just that the slope's constantly changing. It doesn't have a single slope. It just has a changing slope. But some students remembered back from unit 1 and said, you know what? When we had a curve before, we had to linearize it and then make the mathematical model from the linearized version. And so some students did that, which wasn't expected, but was really cool that I saw them do that. When they did that, what they discovered was this. Some students chose to linearize the position time graph in the moving man. For those that did, they found the slope of the linearized position versus time graph was 1/2 the slope of the velocity versus time graph. What is the slope of a velocity versus time graph?
The acceleration.
Acceleration. This equation we just derived is position with time. This time squared, how do we linearize something that's quadratic? You square something. What do you notice is right here in front of the A? A 1/2. So they proved with moving man, when you linearize a position versus time graph, your slope will be 1/2 of the acceleration. That's what you're going to hopefully dig into even more next week when we go back and revisit that moving man graph and do some more graphing with it. So if you have a velocity versus time model, the acceleration is the slope. If you have a position versus time model and you linearize it, you'll have to square the time to make it linear, and the slope will be 1/2 the acceleration. Math is amazing. All right. So that's enough for today. But I want to give you this last 30-ish minutes to work on whatever you need to work on. So let me very briefly talk to you about how to do the test corrections in case that's what you want to work on today. So let me go to Axis. Logged me out, so. All right. So a couple of things. Over here on the announcements, you can see Unit 2 test corrections and retakes. If you click that, here are all the dates and times for the retests that I mentioned to you before. All right. Unit test corrections and the unit test retakes are due by the 16th. And these are the 4 dates and times you can choose to do the retest. I'll just have the Zoom running and you'll log in and do the test. All right. You do have to do the corrections for 2 reasons. 1, if you don't, you won't earn the curve on the grade. And 2, if you don't, you can't do the retest. So it highlights that right here. First, earn the curve score on the test. That's your first advantage. Second, you earn the right to take the retake. Okay, so that is a quick summary of what is expected. Now, if you go to assignments and you click on Unit 2 test corrections, it gives you some directions right here. Number 1, put your name on a separate sheet of paper. Number 2, write out your test corrections on that sheet of paper. For multiple choice, write a sentence explaining your correction. For free response, rewrite your answer with the correct work. 3, carefully number each question clearly that you are correcting. 4, submit the paper in this assignment. All right, so that is what you are to do for your test corrections. If you go to the Unit 2 test, it should be visible now. I published it earlier. You should be able to open it. In the comments, you should be able to see both your original score and what the score will change to if you do the corrections. It says after corrections and gives you both your percentage and your test score. So once your corrections are submitted, I'll change your test score to what's in that comment box. Okay. Any questions about what to do for the corrections or how to submit it or anything at all?
Will they affect quarter 1 grades? Because like some colleges, they want quarter 1 grades for early decision. So like if we do them before Friday, can they affect it?
Yes. If you, anything that's done by this Friday will go into the quarter grade.
Thank you.
So the deadline's not till the following Friday, but if you get it done this week, I'll have it graded this week. Any other questions?
Why does some teacher say the deadline for grade is Tuesday, but for your class is Friday? I'm just kind of confused.
Some teachers are saying it's tomorrow.
Yeah. It's
They probably
like
just want more time to grade. So
Oh, okay.
yeah, I just am allowing through Friday.
Makes sense.
Yeah.
And also I have a question about that moving man assignment that you talked about.
Mhm.
When you linearize the position versus time graph, won't that graph not be position versus time? That would be position versus time squared.
Correct.
So that's why when I was doing it, I shouldn't, I feel like I shouldn't linearize the graph because it's not the same graph anymore.
Yeah, I wasn't expecting anyone to, but I was excited that some thought of that because it showed they were remembering what we did in Unit 1, and it also makes a connection to what we're doing today. So for that assignment, it wasn't really what I was looking for, but I thought it was cool that some students thought to do that because they were connecting some things.
Okay.
Yeah.
But if the student put the answer like that, it's wrong, right?
Well, that wasn't, for most of them, that wasn't the only thing they put, but I think there's only 2 or 3. But they also said because it's the slope is changing, we have to linearize it. So they gave me the answer I wanted, and then they did extra work.
Oh yeah, definitely. Oh
yeah.
Oh, okay, I understand now. Thank you.
Yeah. Yeah, the extra work was above and beyond, not that I was expecting. Yeah. All right, so we're down to about 25 minutes now. You can stay online if you want, and I'll be here. I can answer questions, whether it be about Moving Man, whether it be about summary sheet or your test. I'll just be here ready to help. If you don't have questions and you just want to log out and go work on your own, that's fine. So your choice. If you're taking off, I'll see you on Thursday. If you're hanging around, I'll be glad to help you any way I can.
All right. Thank you, Mr. Webb.